Hi everyone, I'm Ollie McBride from Open Bionics, and today I'm going to be talking about our company, what we do, and why we do it. So we're a robotics company based in the UK, and we specialize in developing artificial limbs for amputees. So today, I'm sure you've met Angel and Jason sort of throughout the weekend. They're wearing some of the latest bionic hands that are available, and sort of they're costing about $100,000, which is just, we think, a bit too expensive. So, and that makes them inaccessible, and so even with insurance, people can't really afford to get them. So at Open Bionics, we're trying to take the functionality of those hands that cost up to $100,000 and reproduce them for about 20 times cheaper. And so we use 3D printing. And so we choose 3D printing over sort of the injection molding and other mass market, other manufacturing techniques, just because I'm sure, as you're aware, everyone's hands are different sizes. So we 3D print a custom hand for every person. So at Open Bionics, our aim is to create and to democratize technology that enhances the human body. So we see ourselves building assistive tech for the masses. We have the robotic engineering skills to create devices that solve a real human problem. So essentially, we turn disabilities into superpowers. So at Open Bionics, we've been running for about 2 years, and over those 2 years, we've won a number of awards. So last year, we won the James Dyson Award for Innovative Engineering. We were at CES and we won the Best Product Innovation. And then we were also named as one of the top 10 most innovative companies. And so why are we sort of winning these awards, and why are we getting noticed? Well, we're doing it differently. We're completely open source, hence the name Open Bionics, and all of our files and software are available online completely for free. So I've met a few people here today that have actually downloaded those hands and printed them themselves. And so we're open source because we believe that a community all working together with a common goal can make prosthetics more accessible and more available. So does anyone recognize this picture? Or at least what's in this picture? So this was a big news story probably just over a year ago. And it was the first 3D file ever sent to space and 3D printed. So NASA sent the file, the STL file of this wrench up to the space station, where it was then 3D printed and they could use it as a proper tool. And so not to one-up NASA or anything, but we sent a bionic limb over email. This is I think he was a Marine vet who lost his limbs in Afghanistan. It's called Taylor, and he found our technology online, all of our open source free files. And with the help of a friend, he downloaded the files and 3D printed his own custom bionic hand in his garage. So this is why we do it, because otherwise he wouldn't have been able to have a custom hand. The technology he had available to him, like his existing prosthesis, just weren't giving him enough functionality, so we made his own. And so we also use the latest in 3D scanning technology. This up here is actually a smartphone with a 3D scanner attachment, so we can scan the amputee's residual limb. Typically, when an amputee goes to get a socket fitted at their prosthetist, they have like a plaster cast session, which can take quite a long time, and the plaster cast heats up as it sets, so that can cause issues with the if you've got a sensitive limb, it can cause issues, and it's quite an unpleasant experience. But with a 3D scanner, it takes us 2 minutes. We can just not even touch the limb, just take a 3D file or a 3D scan of this arm, and we get a 3D file straight away. So we then take this 3D file, import it into our CAD software. We use something called Blender, which is another open source 3D manipulation tool. And we design a custom bionic socket and a custom bionic hand, and then we then 3D print them, and we have it all in 5 days. So what typically takes a prosthetist or clinician about 3 months, we've done in less than a week. And so here are, we've got Nico in the orange, Dan in the middle, and then Grace on the left. And at Open Bionics, we don't just design for amputees, we design with amputees. So Nico here lost his right hand in an industrial accident a few years ago. And he's wearing one of our early prototypes. As you can see, you've got an orange socket, an orange 3D printed hand, and a blue battery that, in that version, it was just cable tied to the outside. He's actually an incredible guy. Since he lost his limb, he's become like a bionic inventor. So he makes robotic hands and robotic attachments just at home. It's incredible stuff. In the middle, we have Dan. And we've actually been working with Dan since pretty much day one. He emailed us just as we were starting the company and asked if we needed a hand, if someone to test all our products and basically give us feedback. And he's worn, I think, almost every single prototype from day one. So he's been really useful to have on board. And then on the end, we have Grace, who is part model, part actress, based in the UK. And she was born with a foreshortened forearm, so similar to Angel, just past the elbow. She's actually wearing a fashion designed hand, so it's got fiber up. Oh. So is that good? Cool. So it's got fiber optics down the arm that light up as she walks, and then it's studded in Swarovski crystals, if that's how you say it. Like thousands of them. It took us, I think, like 3 or 4 days. Is that good again? It took us about 3 or 4 days to put all those crystals on there. We're not going to do that again. And so why are we creating these hands? So this is an actual prosthetic given to a child in the US to wear. It's literally just a lump of plastic, like skin-colored, hand-shaped plastic, and some Velcro. It's like no one wants to wear that. And so this is Logan, a 12-year-old kid that we were fortunate enough to work with just last year in Los Angeles. He was also born with a foreshortened forearm, and this is an actual prosthetic that he was given sort of to wear to school. It's just, yeah, not that useful. And so, like most amputees, Logan wasn't happy with the prosthetics that he had available to him, and this is even through insurance. It's not that great. So we worked with him and other amputees to sort of put like a mood board together of what people wanted, what people could have. And so we asked them, like, what would you want on your bionic limb if technology was not an issue? So for example, it could be a beautician's makeup bag where you've got a mirror in the palm and like a lipstick in the finger. It could be an explorer's rucksack, so you've got a compass and like a laser and a torch, maybe even a lighter. And then it could also be like an artist canvas, like a whiteboard. So completely white arm, and then they can color it in depending on how they're feeling that day. Basically, with a 3D printer and some know-how, you're completely limitless. And so this is an actual cartoon drawn for us by the Marvel comic team. And it's basically, they love drawings and technology. So they were like, here, try and create this. And so this is what we want to try and do. We want to turn kids into bionic superheroes. And so this is one of our renders for the Iron Man hand from Marvel. We were actually the first company to take Iron Man's hand and turn it into a prosthetic, fully self-contained. This is the Disney Frozen hand. It was obviously loads of sparkles and snowy things. And this is my personal favorite. This is the Star Wars lightsaber hand. And it looks pretty cool, but like they're just renders, so we built them. So this is Logan again, wearing the lightsaber hand. And so when he turns it on, it goes like a proper lightsaber. He's actually wearing it in Luke Skywalker mode at the moment. So that's blue. And he can press a button and it will turn off, as a lightsaber does, and turn on again in green for Yoda and purple for Mace Windu. And it's also got an accelerometer, speaker, and vibration haptic motor in it. So when he waves it around and hits it against things, it probably goes and clashes just like the lightsaber toys. It's a lot of fun. And so this prosthetic is completely self-contained. You've got the battery, the lights, all of the electronics are in the hand and the socket itself. And the hand is controlled using something called EMG, which is electromyography. And that works by sensing the electrical impulses from your muscles. So your brain tells your muscles to move down the nerves, the muscles fire, and then we read that potential difference across the muscle. We then amplify it, remove a bit of noise, do a bit of processing, and then can interpret those muscle signals to control the hand. So it's quite a simple system, at least in this version, in that we just read two muscles, your forearm muscles. So when you bend your wrist inwards, the inner forearm muscle contracts, and when you flex your wrist outwards, the outer forearm muscle contracts. So that's two EMG inputs that we use, so you can use that to open and close the hand. And then we say double tap, so if you bend your wrist backwards twice, then it will change grip. So for example, Logan would be in fist grip, where all of the fingers are moving. He'd double tap, and it would change to pinch, so he can do some finer tasks. He can then double tap again and go to tripod, and all of the grips are completely customizable. It's just however they want it, we'll make it. And so here he is using, I think that's tripod grip, playing with a little 3D printed statue of himself that we scanned and printed for him. This is in fist grip, playing with little Star Wars toys. And this is an incredible picture because Logan's never had a right hand, but he's playing with toys like his body's completely adapted to using a prosthesis. And then, so we have, this one's fist grip, and we also obviously put force choke in it, which he absolutely loved, but we had to turn down the power because he kept on killing the guards. And yes, you've got everything in that arm, and the aim for the future arms is to have all of the panels removable. So you could not just have different lightsabers for each day or hour or so, you can put on different characters' arms. So for example, this is Sydney using the Iron Man arm, and she's also playing with a small 3D printed scan of herself. Obviously in the palm there's a repulsor, and as Sydney opens the hand, the repulsor starts glowing. The more she tenses the muscle, the more it glows, so she can then release and fire it. And that's actually a really interesting concept that we were trying out because it could be used for physiotherapy and help increase the muscle mass and stop them wasting away. So that's something we're still looking into to see whether it could be a good tool for physicians. And so this arm also had rockets firing out. There were lights, but when you pressed a button, sort of rockets would flash, it would vibrate and shoot and make noises. So that was a lot of fun to sort of design and create. And so here they are looking pretty badass. And it was amazing, once they put on these arms, they were like running around, showing people, oh, look at my arm, look what I can do, oh, I'm going to force choke you and kill you. And like they weren't shy about it. It was, so typically with Logan's sort of plastic lump that he was wearing earlier, he was a bit shy about it. I mean, it wasn't the most aesthetically pleasing or even fun thing to wear. Whereas when they were wearing these, they were toys as well as functioning prosthetics. So it's like, and they wanted to wear them, which is basically a win-win. And so our aim is to produce prosthetics that kids want to wear. So imagine turning up to school with one of those as opposed to like the plastic hand from before. We've also worked with a few other companies. So this is the Adam Jensen Deus Ex arm from the game, I think Human Revolution. And this is the actual hand from that game. So there's characters in the game that have this file. We then took that file, modified it slightly to put in batteries and motors and the socket, and then 3D printed it for Dan, who you'll see in a minute. And then, so this is the Titan arm, which is a similar arm, but more faceted design, and I think it's the shield from the game. And again, these renders look pretty cool, but the real things look better. So here we've got Dan again, wearing the Jensen arm, And on the left, well, my left, your right, we have the Titan arm. And again, it's incredible to see how natural these arms look. Obviously, they're like your eyes are drawn to them because they're cool designs, but they're using them as if they are real hands. It's so cool to see that. And so Catherine actually had quite a traumatic experience growing up. She was quite shy. She would always hide her arm behind her back. But again, when she was wearing this, she was going around sort of holding her phone in the prosthetic, typing with her other hand, running up to people, showing them what she could do with the hand. It was very cool. And I think this next video is the world's first bionic hand unboxing video.
Hey, I just bought this out of the vending machine and I want to see what's in it, so we're going to unbox it.
And it's incredible to see this as well, because Dan's not even looking at the hand. You could it has haptic feedback, by very simple form of haptic feedback. So he has vibration motors, so you can tell if a force limit is reached or if he's changing grip. And so this is Tilly. She's at 10 months old, I think it was. She lost both of her hands due to septicemia from meningitis. So she had them both amputated. And she's incredible. So she's a massive gamer fan and wants to become a bionic supermodel when she's older, which we're going to try and help her out with. And I've actually got on her arm down here, which I forgot to bring on stage. So this is her actual arm that we produced. And as you can see, it's absolutely tiny. I think it's the smallest multi-grip myoelectric prosthetic arm that's been produced, but I haven't seen many others this size. And so you've got the hand, which is size matched to her other... No, it's not, sorry, that was Sydney. It was size matched to her sister, who is of a similar age. And then you've got this socket here, and this socket has removable panels for the battery. And then it also has the sort of power buttons and all of the EMG electronics for sensing muscle control. And it's charged via USB. So it's quite a cool little device. And so this is Sydney, I think it was a minute or two after she put the hand on. And it's just, we've never seen anyone throw anything with her prosthetic. And that was the first time she's ever thrown anything, because obviously she lost her hands at 10 months old. And here she is, just sort of doing various object testing, just to get her used to the whole control mechanism.
See how good the grip is? Oh,
But she picked it up incredibly quickly.
Grip, isn't it? Yeah, that's good.
And so to control this, she's tensing her inner forearm to close the hands, and then obviously picking up an object. And so she's never been able to interact with those objects in that way before. So it's, yeah, she had a lot of fun. And as we were walking back to the lab from the sort of filming area, we managed to snap this picture of her just holding herself as someone would with two hands. Like, no one's taught her that. It's just her body's adapted to the new tool that she's wearing, and thought that was comfy. And so this is Dan, wearing the DizX arm from before. His favorite grip is to have two fingers and close them like that. And then, again, Tilly looking badass. And so this is our team back in Bristol in the UK. Still quite a small team, but we're all very passionate about making assistive technologies affordable and accessible. And so that's it. I've been Ollie. Have you got any questions? Yes, sure.
What's the future for a full arm? Is that something you're exploring also? Does that still use EMG technology? Because the muscles are different.
Yeah, so for those of you that were here last year, there was a guy called James who I think he hasn't got anything below the shoulder. So we designed the hand that his arm was wearing, basically. And so his arm just had a passive wrist and a passive elbow and a passive shoulder, because the higher up the arm you get, the stronger motors you need, which then adds weight. So yeah, a full arm is complicated, and also the EMG, as you said, you can't have it on a forearm if you don't have a forearm. So we've used the shoulder muscles because you've got quite a dense grouping of muscles up there that you can put sensors on. Another method is something called targeted nerve reinnervation, which simply takes the nerves that would be linking to an arm and then bring them closer to the surface, and then you put EMG electrodes on those muscles that they're now linked to, and then you've got a lot finer control. But as far as how are we developing an arm, it's getting there. So we're starting at the hand, and we're just finalising our wrist development, and then we're going to be going up to the elbow, then up to the shoulder. But yeah, at the moment, the sort of control system is quite limited. Like it's still in experimental phase to have more control. Did that answer the question, or was there any other questions? Sure.
You mentioned haptic feedback for kind of grip sensing. How does that work at the end? Is it vibration?
Yeah, so the socket has a vibration motor in it, similar to that of a smartphone. And you can get the haptic feedback set up for many different things. At the moment, we've just got it on grip change. So as before, if the user double taps their muscle, it will change grip, and we can signal that with the haptic vibration motor. You can also use it for force feedback. So if a force limit has been reached, so for example, if you're grabbing a plastic cup, you could be in a gentle grip mode that will only apply a certain amount of force, and it will vibrate when that force limit's been reached. And then you can also use a different type of haptic feedback, which we've also experimented with, which is like a pressure feedback. So think a servo with an arm that presses into your arm when a greater force is detected. So you've got a variable sort of sense of how much force is being applied at the fingers. So there's quite a few different experiments in that field. It's just which one's going to be reliable enough and useful enough for an amputee to want to use it. So the dual channel EMG, sort of minutes. I mean, we were testing it yesterday. I think every single person picked it up in like about 30 seconds, because it's simply the flexion and extension of what would be the wrist. And for those that don't have the wrist, so for example in Logan's case, he still had those muscles because he has a forearm, and he would actually use those muscles when he was younger to hold some paper while he was colouring in. So he knew how to activate those muscles. Yeah, and it's once you see the hand moving when your muscle tenses, it's very quick to pick up. Anything else?
To try to recognize what used to be the finger actuating muscles that are down in here.
Yeah, it's a.
Almost like a biofeedback in each. Actuate those muscles, even though they don't have necessarily the tendons or anything.
Yeah, it's so yeah. The more muscles you detect, the complicated the control system gets, and also the harder it is for amputees who don't have fingers to pick up and learn the system. Because if they've never known how to use a finger, how to flex a finger, then they have to basically learn that from scratch as a child would when they're growing up. There's a few different technologies for that. So surface EMG, which is the stuff we've got here. If you have multiple channels, like multiple sensors, you can do some complicated pattern recognition stuff that actually Angel was experimenting with an arm she's been wearing. But that is very complicated just because you've got so many different sensors, a lot of processing and stuff like that. So there's also another system that can take like a ultrasonic, it's basically a scan of your arm, and it can visually see how muscles are moving. But then again, if an amputee either has never used those muscles, they're going to be really small and hard to detect, or they're just not going to be able to understand the link from their brain to the muscle. So the dual channel is easy to implement and easy to pick up, but the more sort of metrics you sense, the harder it is for the amputee to control it. Yes, at first, yeah.
Process, you don't have that machine learning algorithm.
Yeah, exactly that.
Teaches them how to use those muscles.
Mm.
To recognize kind of visual things like, oh, you're moving this muscle. This is like moving it, you start individually control those muscles.
Yep. So that's the Deca arm, which is what Angel's doing a trial with at the moment. That does exactly that. I think it's 6 inputs as opposed to our 2, and that's different. So for our hand, we've basically got, if you bend your wrist and activate this muscle, we then close the hand. Whereas the Deca hand is, you do a motion, whichever motion you want, and the hand will then look for that motion next time to control the hand. So it's less of a, yeah, it's just a very different control technique. But yeah, it's very possible and probably will be implementable over the next year or so.
Do you get much pushback from the companies that make the expensive arms?
Not at the moment. We've actually been quite fortunate. So I think one of the CEOs from Bionic has been very helpful in initially when we were starting this project, and sort of gave us a few components, like, oh, you might need these are expensive, take a few of these. So they've been really helpful initially. But I'm sort of assuming they were expecting us to fail because it's a very complicated sort of device to create. And especially, like, there's a reason that theirs are expensive. Obviously, there's other things to play, but the components are expensive. The motors are really expensive. Carbon fiber, or a custom carbon fiber socket is expensive. So there's a reason theirs are expensive, but we just think we can do a few different techniques to make it cheaper. And in theory, we might not trample on each other's feet too much, because if people want a super expensive, probably more functional hand than ours, because it's metal, so it's going to have a bit more strength than our plastic and rubber hand. Yeah, so we haven't had too much resistance yet, but I'm sure, yeah, there probably will be some.
What do you do when the kid is growing? Do you replace the arm? What's the process?
So so typically, especially for a growing child, they grow out of their prosthesis in about 9 to 12 months, which is another reason why children aren't really able to wear the more expensive arms. Because imagine having to pay £100,000 every year, maybe even twice a year. But so for our system, it's obviously cheaper and 3D printed, and we use a 3D scanner. So we, after the initial design, printing, and implementation of the hand, we then give that to the user. When they feel they're growing out of that hand, we ship them a new scanner, sort of just like send it to them via post. They then do a 3D scan themselves, send us back the scanner, and we just 3D print the new components. So it's typically a socket and a hand so it would be a socket, say, every year or so, and a hand maybe every 2 years, 3 years, depending on how quickly they're growing. And so they'll send back their existing hand. We'll take all the expensive components, like the motors and the batteries and the electronics, put that into the new hand, and then ship it back to them, just so it gets cheaper the more they use it. Any other questions? Nope. I mean, I'm going to be down here for the next 10 minutes or so, so feel free to pop by. Cheers.